All right, so what I would like to talk about now is a particular aspect of the C++ standard. So when you write programs, then one of the things that you often find in software is that there are many things that are almost the same, but not quite. So for example, you might have a vector that stores double precision numbers. That would be, for example, 8-byte per floating point number. And oftentimes you would want to compute, let's say, the L2 norm of this vector. Let's say the sum of the squares of the elements and then the square root of this. So you could write a function for this, and it would, let's say, add up the squares of all of these entries and then take the square root at the end. But now what happens if instead you have another data type that actually doesn't store double precision entries, but single precision entries, so only 4 bytes per floating point number? If you want to compute the norm of this kind of vector, you would have to rewrite the entire function. You would have to just duplicate the body of this function, and where you take the square of double precisions, you would now have to take the square of single precision numbers, and at the end take the square root and return a single precision number. And of course that's burdensome because the functions are exactly the same. The content of these functions is exactly the same. There is absolutely no reason why we should be writing the same function twice. It does exactly the same sort of thing, so why write it another time? And of course in mathematics we have that very same problem with regard to the space dimension. From a mathematical perspective, the way we write our formulas for the finite element method looks exactly the same if we write it in 2D or in 3D or in 1D. It doesn't make a difference. The mathematical notation goes exactly the same. So when we write, for example, the gradient of a function, what we mean by that, if this function is in 2D, the gradient has two components, the x and the y component, or x and the y derivative of u. Whereas if we happen to be in 3D, then it will be a vector with 3 components, the x, y, and z derivatives of u. But we use the same symbol. We just use the nabla operator, the upright triangle. And so this is an example of where in mathematical notation we do not make a difference between things that really are different, that are either 2-dimensional or 3-dimensional, but we don't make a difference because the meaning of these sort of objects is the same. And so that is a case that has found application in programming in C++, where we try to use one of the C++ features that we call templates to make our lives a lot easier on how to actually implement these sort of things in such a way that we can run things in 2D and in 3D. Because basically we can write the code in exactly the same way if we use these features cleverly, and then write the program only once and run it either in 2D or run it in 3D. And we'll come back to this in the next lecture on step 4, where I'm going to show you how we use this feature. So you've already seen this in the first few lectures where we talk about, for example, triangulation, and then in angle brackets we had 2 or 3. Well, actually I showed it only in 2, but the same program will run again will run as well if you replace all of the angle brackets 2 by angle brackets 3. So I would like to introduce you to this feature that's called template in C++. So templates is a rather complicated feature in C++ that if you look at the C++ standard, you will notice that on the order of 70 to 80 pages of the standard are devoted exclusively to the description of templates. So it is by no means something that is easy to understand if you really want to know how it works. But it is not a feature that is very difficult to understand conceptually. And so what I'm going to show you essentially is a conceptual understanding of what templates do. I'm not going to explain to you how the compiler translates a template into actual code for a machine to execute. But I'm going to, let's say, try to explain how you need to think about templates, and from there it will be relatively obvious for you to understand how to use it. So the motivation, as I said, goes like this, that in C++ we have this way to express things that are similar only once, even though they're not quite the same. And that we would like to use this to represent the same thing that we do in in our mathematical notation where we have the same formula and it means, or it represents different things even though they have essentially the same meaning in different dimensions. And here are examples for this. So if you look at the matrix assembly, for example, that we had in step 3, essentially what we had is we had a loop over all the cells, a sum over all the cells. Then we had a sum over all of the quadrature points, and then we needed to apply the gradient, or we needed to sum up the dot product between the gradient of phi I at these quadrature points and the gradient of phi j. And what these gradients are, of course, is different in 2D and in 3D. But this formula represents something of the following kind. So we would like to have a for loop over all the cells. The cells too are different, of course. They're quadrilaterals in 2D and hexahedra in 3D. But we would like to write it in such a way here, and then we would like to apply a d-dimensional quadrature formula to the integrand on cell k. Another example is one of the typical mesh refinement criteria that we're going to use is called the Kelly error indicator. And it essentially does something like this. So on every cell k, it computes the mesh size of this cell over 24, and then it's going to integrate something, namely the jump of the gradient between two cells over the boundary of this cell. What exactly this does is not all that important. The point I want to make is that we need to have something of the following kind, namely a loop over all the cells, and then a loop over all the faces of the cells. So in 2D, this would be over all of the 4 edges of a quadrilateral. In 3D, it would be a loop over all the 6 faces of a hexahedron. And then on each one of these faces, we would like to apply a d-1 dimensional quadrature formula. d-1, that would be in 3D, a 2-dimensional quadrature formula over the faces, and 2D, a 1-dimensional formula over the edges of a cell. So our mathematical notation doesn't make a distinction between 1D, 2D, 3D, but of course the data types that are represented here are going to be completely different, right? I mean, a 2-dimensional face is not the same as a 1-dimensional face. And so we somehow have to represent this in our software in such a way that hopefully we do not have to write the same code twice, or 3 times if we want to run it in 1D, 2D, 3D. So the way these templates work, let me try to explain this with a simple example. So let's say I had a function that just computes the square. And of course I could write a function that takes a double precision and returns a double precision. And that would be easy enough to write. So it's a function that takes, for example, a double x and just returns x times x, and the return type would also be a double. But then if I want to write the same function again for, let's say, a floating precision or for an integer argument, I would have to write a function sqr for square again with a different argument type and a different return type. But the body of the function is exactly the same. It's still going to return x times x. So why should I write it twice? If I have to write it twice, my program becomes bigger. It is more error prone because if there's a bug in one function, I would have to fix it in all of them, and so on and so forth. So what C++ offers is something that is called a template, and it works like this. So I marked this whole thing here as a template, and there is an argument to template, which in this case is a type name, and the argument is called number. So this is just like when you write a function, for example, where in parentheses you write argument double x, for example. That would mean that the variable name is x and its data type is double. In this case, the name of the argument is number, and what it represents is the name of a type. Okay, so number is the argument of the template, and so what this template thing here does is it takes an argument of type number, which is not specified so far, and returns a number. And so x has data type number, and we return x times x. So the point that's important in all of this is that this is not a function, right? This is not the same as if I would write double sqr const double x return x times x. Rather, it is a description how the compiler can generate a function if I told the compiler what number was. So here's an example in this use case down here. So if I declare, for example, two variables, x and y, and they're both of type double, and then I write x equals square of y, then what the compiler is going to do is it sees sqr y, and it knows that y has data type double. So it will try to find a function sqr with a double argument. And it will find, lo and behold, I don't know any such function. Nobody defined a function that takes an argument of type double. So the next step that it would do is it would see, do I know of any templates where if I replaced the template argument by double, that I could come out with a function that takes a double as an argument. And that indeed does exist, because the compiler has seen this declaration of this template up here, and it will see, okay, so I want to call this with y, which is a double. So what if double, if this number argument here was actually the data type double? Could that work? And the answer is yes, of course. So if I replace number by double, then the arguments match. And so what the compiler is going to do is it's going to take this template declaration or template definition here, is going to replace number everywhere by double. And so in other words, it generates a function out of this template. And this function will return double, will take a double as an argument and return x times x. Okay, that's exactly what I wanted. Now, if at a later point, let's say you have additional variables a and b that are also of type double, and then you call a equals sqrb, at that point the compiler already has seen that there is a function sqr that takes a double, namely the one that it had previously generated out of the template, and it doesn't have to do it again. But if you called, for example, sqr b, where b is an integer, then it would find, okay, well, that's nice. I know a function that takes a double as an argument that I had previously generated out of this template, but now I need a function that takes an integer out of this as argument, and that I don't know. So it will go back to the original template and do the same step again. It's going to see, okay, I need to call it with an integer argument. What if I replaced number by integer? Can I match all of the arguments? The answer is yes, and it would create a second function that returns an integer that is called sqr, that takes an integer and that returns the integer times itself. Okay, so if you call sqr with two different data types, it's simply going to create a second function out of this general template. We call this process instantiation. So instantiation generates an actual function out of a template. And you see how this saves me a lot of time, because I really only have to write this function once and then let the compiler do the job of duplicating it. If there's a bug in there, I fix it only once, and the compiler will propagate it into all of the places where I call this function with different arguments. I can do exactly the same thing with classes as well. So for example, you could think of having a vector that stores 3 elements. So you might think of this, for example, as the x, y, and z coordinates of a point in 3-dimensional space. So maybe I want to store these coordinates as double precision. Maybe I want to store them as integers. That's sort of my choice. Sometimes one might be a better choice, sometimes another one might be a better choice. In either case, the way I'm going to write this is as follows. So I'm going to write myself a class template that I'm going to call vector3, and it's going to store an array of 3 elements of type number. And I'm going to prefix this with template type name number. So as before, this is not a class. It is a description how the compiler can generate a class out of it if I told the compiler what this data type number should be. Now here's how I do this. So for functions, it could deduce the argument from the data type of the argument. So it could deduce what number should be from the argument with which I call this function. Here I don't have that luxury, because if I create a class, there is no call involved, so I have to be explicit. So if I use a class template, the only way I have is that I explicitly say what the argument should be. So I do this in these angle brackets, just like you've seen for triangulation 2 and triangulation 3. It's essentially the same. So this one, if I write vector 3 square brackets double, or angle brackets double, then that means it's going to create out of this template a vector 3 that stores 3 elements of type double. And that is, of course, an entirely different class than if I had, for example, said vector 3 int. And consequently, a vector 3 double and a vector 3 int, they're different classes. They're not convertible into each other. These are separate things. You should not expect that they behave in any other way than any other two completely unrelated classes. Just because they come out of the same template does not mean that they're derived from each other or related to each other. They're separate classes. The advantage of this one is, so if I do it like this, for example, then at compile time, so when I actually write this one here, the compiler, of course, knows at this point that the elements are of type double and that there's exactly 3. And so if, for example, I compute something like the norm of this vector, it can optimize based on this. There's other things that I can do with this. For example, I can use a device that is called explicit specialization. So let's say if I want to go back to this vector 3. The way I do this in here is that I store 3 separate elements of a particular data type number. And so that's appropriate, for example, for integers and doubles. But let's say if I wanted to instantiate this vector 3 with a bool. So the size of a boolean is, on modern machines, 4 bytes. Of course, in reality, out of these 4 bytes, I only use a single bit. So it's a little bit wasteful. I store 32 bits in memory, even though I use only one single bit. And so one of the ways that I have is I could, for example, represent a vector 3 where the argument is bool as just a bit field that needs 3 bits. In this case, I could, for example, represent this by an integer. There are better ways to do this than to use an integer, but that's just an example. So what I'm doing here is I'm saying, well, this is an explicit specialization, so it is a template, but then it doesn't have an argument list. So essentially this means it belongs to the same family of templates, but it is the class to be used if the argument of the template happens to be equal to bool. So what this does here in this case is it really is a class, right? It doesn't depend on an argument like type name number anymore. It really is a class. And so when I have code like down here where I say vector bool, or let's say vector double, that takes the instantiation out of the general template, whereas if I write vector bool, it actually takes this particular class. Okay, so I've shown you how to do this with type arguments. So I can have templates that depend on type names that I can replace, for example, by double or by int. And I can do this for classes, or I've shown you how to do this for functions. I can do this in C++ not just for arguments that are type arguments, but also for value arguments. So oftentimes what we do is we take a template, for example, that as template argument would have an unsigned integer, a number. So if you wanted to have a vector of n elements, for example, you could write it like this, right? And when I write vector 3, then that would mean that I produce a vector with exactly 3 elements. If I had written vector 5, then that would be a vector with exactly 5 elements. So in this case, the template argument is actually a value, in this case, an integer number. And what we're going to do in deal.II, of course, is we're going to make a lot of classes templatized on the space dimension. So what can you do with this? For example, here's something that computes the norm of a vector n. So this is, again, it's a function template. It's not an actual function. It is a template of a function where if somebody told the compiler what n is in the argument, so if I pass, for example, a vector 3, then it's going to replace n by 3 and can convert this template into an actual function by a process of instantiation. And what it does is, well, it initializes a temporary number of 0. It loops over all of the elements of this vector, takes the square, adds it up, and in the end returns the square root. Now, the benefit of this is, let's say, if I tell the compiler to do this for n equals 3, it will know that it's wasteful to actually write down the loop. What it really should be doing is just look at the first, second, and third element of this loop and add them together without the overhead of a loop. So it's just going to copy the call to SQR 3 times. That's an optimization the compiler can make based on this. In deal.II, the way we use these templates fairly frequently goes like this, that the value argument that we use is actually the space dimension. So for example, to represent a point in dim dimensions, we created a template class that we call point. You've seen this in step 1 and 2 already, and you will see this throughout the entire library. So it's a point that is templatized on the space dimension, and it stores dim components. So if dim was 1, it would only store one coordinate, namely the x-coordinate. If dim was 2, it would store 2 coordinates, and so on and so forth. And then based on this point template, you can build all sorts of objects. For example, you can build an object of structural dimensions struct_dim in space dimension. So for example, if you wanted to build a line in 3D that would have structural dimension 1 in space dim equals 3, whereas a square in a 2D domain would be a trier object 2, 2. Okay? So what do we need for this? Well, we need, for example, a function vertex that takes the number of the vertex as an argument and then returns a point space dim. So let's say if you had a trier object 1, 3, so struct dim equals 1, space dim equals 3, then you would have this line in 3D, and of course the endpoints, the 2 vertices that define this line, would be 3-dimensional objects. So it needs to return a point space dim. How many points do I need to store to characterize such an object? Well, let's say if you have a structural dimension of 1, that's a line, you need 2 endpoints. If your structural dimension is 2, you need 4 vertices. That's, for example, a quadrilateral. You need 4 vertices. If you have a structural dimension of 3, you would have a hexahedron. You need 8 vertices. So it is 2 to the power of struct_dim. And in C++, we represent this by, so 2 to the power of struct_dim is 1 left shift struct_dim that takes the number 1, which is in bit representation 0, 0, 0, 0, and 1, and shifts this 1 struct_dim bits to the left. So if you shift it by 1, you get 2. If you shift it by 2, you get 4. If you shift it by 3, you get 8. That's what this left shift operator does here. This left shift operator is to be understood literally in the sense of moving bits over to the left. So this is sort of the, let's say, conceptual way how we represent objects, geometric objects in deal.II through these templates. Then you might have something like a cell, for example. A cell is a particular object, namely that's an object for which the space dimension equals the structural dimension. Okay, so a cell in 2D would be a trier object 2, 2 because it's a 2-dimensional object in 2-dimensional space, whereas in 3 dimensions a cell is a 3-dimensional object in 3-dimensional space. So it depends on only one template argument, and it would have all of the properties of a trier object where the structural dimension and the space dimension is the same. And it could, for example, return to us something like a neighbor, or it could return to us a face, and a face is a trier object that has a structural dimension 1 less than the space dimension and lives in space dimensional space. These are the sort of things that you can do with this. There's also things that you can do with local type diffs. So oftentimes what you want to do is, I've already shown you how you have these loops over all the cells, and there are equivalent loops over all the faces, for example. So you would want to have iterators that either go over cells or faces. And for example, in 2D, you would define this like this. So you would have a explicit specialization of the triangulation class. This is not how it really is represented in deal.II, but it gives you hopefully an idea of, let's say, conceptually how this works, that a cell iterator is some kind of iterator thingy that loops over cells in 2D, whereas face iterators iterate over objects that are one-dimensional in a two-dimensional space, namely lines in 2D. Whereas if you're in 1D, so triangulation 1, it would have cell iterators that go over one-dimensional cells, but there is no face iterators, because faces are things that you want to integrate on, for example, so they have to have an extent, but endpoints of intervals do not have an extent. So there's nothing like a face iterator in 1D. That actually is not true either anymore, either in deal.II, but conceptually you get the idea of how these sort of things are done. So just to give you a brief example of how to use this in reality. So let's say, for example, I wanted to write a function that outputs all of the cells, or let's say the vertices of all of the cells in deal.II. One of the things I could do is I could write myself a template. Okay, so this is not a function, it's a template that takes a triangulation dim as an argument. And what does it do? Well, it loops over all of the iterators, over all of the cell iterators of this triangulation. Okay, so I define myself a cell iterator. Cell starts at tria.begin, it ends at tria.end. It increases every time the iterator by 1. And then it loops over all of the vertices. Well, how many vertices does such an object have? That's given by geometry info dim. Okay, colon vertices per cell. So that's our way of writing this in a dimension-independent way. I don't have to say that it's 4 or 8. And then every time I'm going to output the coordinates of the vth vertex. So as I said before, this is not a function. This is a way how the compiler can create a function. Namely, if I pass, for example, a triangulation 2, the compiler will realize that it can produce a function out of this template by replacing dim by 2 everywhere in this function and compiling it. If I pass a triangulation 3, it can produce a different function out of this template by replacing dim by 3. There's other examples all throughout deal.II. So here would be one where I have to integrate this error indicator, for example, over the boundaries of a cell. So I would need to have in dim space dimensions, I would have to have a dim minus 1 dimensional quadrature formula of type Q Gauss, for example. I have these cells that loop over all of the cells. Then I have a loop over all of the faces of this particular cell. And then I'm going to integrate on a face cell arrow face f that returns to me the equivalent of something like a tria object dim minus 1 comma dim. And I apply the quadrature formula there. So I hope you get the idea of how these templates work. In practice, C++ templates are often pretty clumsy. The syntax that you use is not particularly pretty. And oftentimes what you will find is that the compiler errors that you get if you do something wrong are really, really awkward. Sometimes pages long. So templates is certainly not a panacea. But it allows us to write ways in such a way that you can code your application only once, and it will run in 2D and in 3D. And that has the really huge benefit that you have to debug your program only once, that you can test it in 2D where everything is fast, and then you can do your production runs in 3D with exactly the same code, and you already know that it's going to work. So all I want to say with this slide is that if you're unclear exactly how these templates work, consult your favorite C++ book. So one of the ones that I've showed you in the very first lecture is the book by Stroustrup. There is also c++.com online, and there's a few questions answered in the deal.II FAQs that you can get to from deal.II.org that give you more information about how templates actually work. With this, we'll leave it for templates, and then we'll come back to step number 4, which uses templates to solve the Laplace equation both in 2D and in 3D, and uses this facility to write code only once, but solve it twice.